All right. So, hello and welcome back to the next lecture in the ongoing series of lectures on color reproduction in pre-press repro technique. So, in the last class, I think we had discussed about the various methods through which we can analyze graphically the nature of reproduction and what inferences we can draw if a plot stating the density of the reproduction with respect to the density of the original is given to us. So from that graph, what inferences we can draw and how to analyze and assess the quality of the ultimate reproduction with respect to the original, where it is lacking, which part is good, and some of the I think we can take decisions based on those inferences on how to correct such discrepancies. Some of the corrective actions have already been discussed with you earlier also, but in this class also we will be focusing in these, as I told you, maybe 4 to 5 lectures we will finish this up. So in these lectures also we'll be talking in detail about how to analyze those. Now, as I've already stated in the previous lecture also, that what is the primary goal of any reproduction, right? Uh, the image that you see in front of you, this is basically a grayscale. This can be called as a grayscale. Why it's a grayscale? Because it has got a multitude of wedges increasing in the dot percentages. Okay, so if I ask you that in under what situation or what is that condition that will help us to draw the conclusion that yes, the print production that has taken place and afterwards the reproduction that I have in front of me, that is a good reproduction. This will be this can be only said when the grayscale that appears in the original as grayscale appears as the same in the reproduction, in the printed reproduction. Okay, so there again I would like to draw all of your attentions to the term that is contrast. If you remember the term contrast, that was very interesting. It said that the tones that are there in the original are represented as such in that of the reproduction. If lesser number of tones are being reproduced, then the contrast is lower. If greater number of tones are being reproduced, or even the same number of tones are reproduced, then we say contrast is okay, or contrast is high, or contrast is okay, respectively. Right? So this is what contrast is. We had also defined the relationship, mathematical relationship between the contrast. So in a characteristic curve, or a not characteristic curve but tone response curve with the density of the reproduction versus density of the original, the contrast may be given as the slope of the straight line section. So that is what contrast is basically. Okay. Now, considering this particular condition to be fulfilled, how to analyze whether the grayscale has been reproduced as the same grayscale in the reproduction also? For that again we need to go back to our graphical analysis of the reproduction. So how can it be done? So I'll give you this image. Although this is an ideal situation, basically this never happens. I'll show you a real life situation, real life plot, but I just want you to understand something from this. What is our intention? Our intention is to find out whether the reproduction that has taken place is uh, well enough or good enough or not. That is our reproduction, right? So the thing is, how can this be achieved? How can we do this? What can be done is, if while printing, now you may ask me a question that okay, you have been telling us all the while that you measure the densities of the reproduction versus density of the original, that is all well and good, but how do I do that? Because there's a practical problem. You see, any given image, okay, so I'll just find out some image from the slide itself. If I do have some image, okay, so let us take an example of this image only. Okay, see this particular image, right? You have been designated to print this particular image through your machine, but after printing, you tell me, is it possible for you to find out the density of each and individual point in this image? Can you prepare a curve or a tone response curve from this image? It is not possible like that. Why? Because where first of all you need an area to assess, right? So for example, you have individual sheets also. Individual sheets meaning one sheet for cyan plate, another sheet for magenta plate, etc. So even in that situation, you will have this tonal variation throughout the image. Now, which area do you think? There is no way of understanding which area is having how much dot percentages. It is like searching for a needle in a haystack. You think that this area is having 90% dot, but it turns out that this area is having 90% dot. So your density measure, if you measure density in this region and consider that to be 90% dot or shadow dot, then it will give you erroneous reading. So this is not the process of measurement of densities. What we actually do is we attach a kind of step wedge. We attach a kind of step wedge. This is basically called as step wedge. Why step wedge? Because you see, from one wedge, the individual components are known as wedges basically. Okay, this is one wedge, this is one wedge, like this. So from one wedge to the other wedge, there is an increase in dot percentage. Hence, if there is an increase in dot percentage through Murray-Davies relation, we also know there will be an increase in the the density also. Converse of the Murray-Davies is also said that if there is an increase in the dot percentage, then definitely there will be, that means when fractional dot area increases, density also of the half tone increases, right? So density will increase from one end to the other end. So now you see, if I place this image, I basically place this not image, but I place the step wedge, that is grayscale, in any during within the image that I am actually going to print. So let me show you one example. I'll just get one image for you to see so that you understand how it is done. So as I was saying, let us take a look at how it is basically achieved, how density is basically measured. So for example, this is basically your image that you want to print, okay, through color. Now, while printing this within the sheet or while preparation of this image, you add this particular grayscale within that image itself. Okay, so if you do that, individual color patches, basically one for cyan, another for magenta, another for yellow, another for black, or even for your 3 color or 4 color superimpositions also, what do you get? You will get density from highlight area to density of midtone area to density of shadow area. So you can basically assess how much inking is basically done within that particular image, and what is the variation of densities from the highlight to midtone to shadow area for the printed reproduction. Albeit, you must also have the change in or the variation in densities in the original as well, right? So if you have both this data with yourself, then definitely it is possible for you to compare the change in density and plot the changes in density in the graphical manner. If you do this, you will end up with a plot like this. So let us understand what this plot is. There is a concept in proofing. I will be talking about proofing in the end of this particular lecture series on pre-press repro. That is our final unit. There is this concept which is known as progressive proof. Okay, so I'll just explain what progressive proofs are. So during uh, okay, first of all, let us understand what a proof is. Proof is basically a printed image which is used for analysis purpose and which is later on used for identifying what is the maximum possible image that is capable to be reproduced using our print production or using the manufacturer's print production method. So for example, if your customer or client has given you uh, an original, be it in digital form or in analog form, whatever it is, you make a proof of it. Proof is basically a print itself. You either make a proof out of it, okay? You print it, and you print it in a way which enables you to identify what is the maximum capability of your printer, right? And then you show it to the customer, and if he approves it, then it is basically known as a contract proof. While the concept of progressive proof is that you get individual proofs. So for example, one proof for the cyan plate, that means one sheet will contain only cyan printed areas, another will contain M, Y, K, uh, you know, additions basically. So you get individual and combinations of inks printed on individual sheets. So the first sheet will contain only cyan areas, second sheet will contain only magenta, like this. You see over here there are 7 to 8 number of proofs are basically made using this combination of inks. So ultimately, through this method also, you can do what? You can get not only a print where all the four colors are used, that means CMYK are used, but you additionally prepare some prints with only, so one you have a print which contains all the four inks, right? CM, Y and K. You prepare the second print which contains only three colors, that is the three primary subtractive primary colors, that is C, M and Y. And the third proof or the third print that contains only the black areas. Now you may ask that what is the necessity for this. Now if you understand this plot, then you will be able to analyze and understand finally that why three types of prints are basically required. So you see, this, as I told you, this is an ideal situation. Now normally in ideal situation, what you will see, that you will get a straight line for four color print. The what you have plotted over here. So let me just erase this part basically. Okay, I'll just erase this part. uh, no, I think these options are not available right now. Okay, doesn't matter. Okay, so let us see now here. Okay, now see, normally the our in ideal situation, our print, that is our reproduction, when we plot the density change of reproduction with respect to the density change of the original, we should get an ideal 45-degree line passing through the origin. So this is your ideal curve, right? The C curve that I have that is drawn over here, right? Now, how did we get these densities? What we did during the four color printing operation, we added those color bars, we added those grayscale within the print, and because each of the color bar or the step wedges have got different dot percentages and thereby different densities, we just measured those densities and plotted those density data in the reproduction, that is the printed sheet, with respect to that of the original, right? So thereby we get this straight line. Similarly, for the three color separation also, we get a print where we have printed only using cyan, magenta and yellow inks. So for that purpose also we get this type of a curve, and another curve we get only for the print containing the black ink only, right? So this is that type of curve. So this is how a curve is basically generated. Now the most important thing is what to draw, what inferences to draw from this. You see here, the three color density curve over here, that is curve A. This particular curve seems to be drooping down as it moves from the midtone towards the shadow areas, right? That means what? That means when they are going to get superimposed on top of each other, their densities are basically getting reduced and they are not following the ideal curve. Normally, in ideal situation, we were expecting that the three color superimpositions would have your would be sufficient enough to create an ideal black. But is it what is happening? Is it what is happening with this particular curve? No. Now the question is why. I think you already know the answer to the question why this is not happening. You see that our subtractive primary inks, they are all having some hue deficiency. Because of this, and there are other problems like additivity failures, proportionality failure. So for all these problems that we have already discussed in the previous classes, the three color superimpositions will never create a full black or ideal black. It will always create maybe a tinted gray, maybe a reddish gray, something like this. So it does not create ideal black. So what to do? For that only we had to introduce the fourth printer, that is the black printer. Now you see what is actually happening. You can say the curves A and B together, if in some way, if you combine the curves A and B, you are supposed to get the curve C. Now the question is, why did not we get the curve C with three colors? The answer I have just answer to that I have just told you now. Because of the hue deficiencies, because of the problems of additivity failure and proportionality failure, we are not able to get ideal black using our three subtractive primary colors. That because that is why it is not possible, and that is why it is deviating from ideal behavior. So ultimately what is happening, we are adding a additional fourth printer, that is the black printer, in order to overcome these deficiencies that exist inherently within the your subtractive primary inks. Now naturally our expectation is that, so if we add up the curves for densities for A and B, curves A and B, we are supposed to get the densities of the curve C, that is the resultant curve, right? So now let us see what the black printer or fourth printer is doing. See, the black printer, it's very interesting to note over here that the black printer is starting from somewhere in the mid-tone area. It is, the black printer is not printing in the highlight area much. Black printer is not, you see, there is zero density for the black printer in the highlight to the mid-tone area, but it is only starting to print from where. And another very interesting thing, if you notice, the black printer is starting to print exactly almost from the area where the three color superimposition, three color prints are deviating from their ideal behavior, and their densities and the contrast is basically drooping down. Exactly from that region, we are adding the black, and we are replacing, we are basically adding the fourth black printer, so that the deficiencies that inherently exist in these three colors are overcome and compensated by the fourth printer, that is the black printer. So wherever there is a deficiency in the three color superimposition in creation of the black, we are adding a fourth printer, that is the black printer, in only those areas, that is from midtone, mainly in the shadow areas. You will see that ultimately leads to the creation of a good reproduction. And when we add these two densities, ultimately we will be seeing that the we will get an ideal four color reproduction. But again the question is, do you think that if we add the densities of three color reproduction with the black reproduction, are we supposed to get the density, ideal density that was supposed, that we expected? So for example, if our three color density is basic, so here three color density is 1.5 and our black density is 0.5. Okay, now do you think the resultant four color density will be 2? It will not be 2, it will be lower than 2. Okay, so why is it lower than 2? Tell me that. I have already given the answer to this question before. It is because of additivity failure. What is additivity failure? Additivity failure states that the density of the combination through a particular filter is never equal but lower than the density of the individual links through the same filter. And the reasons I have explained in great detail in the earlier lectures also. So because of these problems, basically you can understand that why no matter how much black we add, if we combine the three color densities with the black density, it will never be equal to the four color density as per our expectation. That means as per our expectation means what? That is your ideal four color behavior. It will never be the same. Okay, this is one thing. Now another thing that I wanted to mention over here is that as I've already told you, that this is showing your ideal behavior, because you see the four color representation or even the three color representation, three color densities are starting from 0. What does it mean? What does the if your plot starts, if your curve starts from total response curve starts from 0, what does it mean? That means it is able to reproduce the 0th dot also. A 0th dot means, I mean, after 0th dot, right? So is it possible, as I think I have highlighted this on this issue in the earlier lecture also. Do you think this is possible? This is not possible. In reality, it is not possible. We are we have accepted the fact that it is not possible for us to achieve 5% to 10% of the dot. I mean, not 10% of the dot, but at least 5% from 0 to 5% dot can never be achieved. We have accepted that fact. And in the next slide, I will show you another plot which is a more realistic plot where you will see that the density, I mean, tone response curves are starting not from 0th point, 0th density, but it is starting from a density greater than 0. This means that we are unable to print that 0 to maybe 0 to 5% dot or 0 to 0.2 density range, and only after that density range, whatever dot comes after that dot percentage, from that we are able to print. Why is that? Because there is dot loss in these regions, in highlight regions, because the dots are so fine, so small in size, be it your flexographic dots or your offset plate dots. We are not able to reproduce that even in the plate, or ultimately they are not getting transferred onto the paper. So because of all these factors, this behavior is an ideal behavior. The second important point that I want to mention over here, because this is going to be of much importance when we talk about ink optimization in our next semester. You see, because the black is basically used to compensate for the deficiencies that exist within the three color subtractive primary color inks, we are not printing black everywhere. We are printing black where it is necessary. Now, where is it necessary? It is necessary based on the nature of your three color tone response curve. Now, for example, if your three color response would have been like this instead of like this, so we automatically would have started the black like this, like this. Instead of starting black from this particular point corresponding to the point where the three color densities or three color tone responses started to droop down, we will now start the adding the fourth printer in those areas, mainly in the shadow areas over here, where it corresponds to the point from which the three color density starts to uh, droop down and the contrast reduces. So what does it mean? We are not going to use the black printer everywhere, right? The reason I will be talking about in detail in the next slide also. We are using black as the black printer as a method to compensate. Remember this very importantly. We are using the black printer as a method to compensate for the deficiencies that are inherent in the three color subtractive primaries, right? So in order to do that, we don't need to put black everywhere. Black is the most dirtiest color of all because it prints the most heaviest of all. It is most easily recognizable through our human eyes. So if you print excessive of black, what will happen? The effect of the other colors will not only get reduced, but overall sharpness of the image, that is also going to get down. The contrast of the image, the image will, instead of contrast of the image getting higher, it will actually drop down because you are going to print a very flat kind of an image if you print black everywhere. Okay, so because of all these problems, we are printing black only in certain areas. Which areas? Mainly in the shadow areas where we need to compensate for the lack of additivity of the three colors. Due to this, black is sometimes referred, this type of black addition is sometimes known as skeleton black or skeletal black. Okay, so I'll be talking about wide black, I'll be talking about narrow black. So these are all terms that are associated with your ink optimization. So various techniques are there. So I'll not talk right now. Later on, I'll be discussing about that. But ultimately, if anyone asks you why black is known as skeleton black and what is the purpose of adding black in your reproduction, that hopefully is clear. Now it is also important that why we refer to black as K. Black is we always write black as K in CMYK. So I have heard people say that if black would have been written as B, it would have been confused as blue, but it is not such. The reason black is referred to as K is because it is a key color in print reproduction. Why it is key color? Because it determines the overall contrast of the image. How so? The example that I just gave you, the amount of black that is essential to be added to any print reproduction process is variable. It is not fixed. It depends on the nature of the three color reproduction. If the three color reproduction is very good, then we have to add black in only those areas where we need to, compensate for those deficiencies. Hence, black is key in improving the overall contrast of your four color reproduction where there are certain deficiencies that exist with your three color reproduction. It is the key color which is not only important, but it is most importantly variable and does not have a fixed value in every print production. We do not have a fixed universal value for the black printer that okay, for all reproductions we'll use only 30% black in the shadow areas. It is not that. It is variable, and it is key. It is one of the key colors in identifying in improving the overall contrast of the print reproduction. Okay, so these are some of the inferences that I wanted to talk about through this particular plot. Now coming to our next plot, it's a very important another plot. This is more of a realistic plot. If you see, why do I say it's a realistic plot? Because of two reasons, primarily of two reasons. I was not talking about the problem with the three color or black reproduction over here, but I talked about one important point. First of two important points really, I said that the four color reproduction is almost a straight line, 45-degree line, right? And that it starts from zero earth density. So because of these, I could easily identify this is not a realistic plot. This is more of a kind of a ideal plot, just to make you understand some of the basic inferences that can be drawn from such a curve. Now this, on the other hand, is a much more realistic curve. So here you see, we see that the entire plot, all the plots basically starts from a point of having density 0.3. That means we have a loss of a density loss of 0.3, right? Why? So if I ask you, in the density range of 0 to 0.3, what is this area? Is it shadow, highlight, midtone? It is highlight area. So we see over here, we have lost 0.3 density range in the highlight area. This is expected. We were expecting this to happen because the dot loss that exists in the highlight areas, that cannot be compensated in any way, because we are not able to print those level of fine dots in any of the printing processes. So because of that, this plot first of all starts from a density range of 0.3 approximately. Okay, now come back to the four color reproduction. Now for the four color reproduction, do you think this is a 45-degree line or even a straight line? See, it's drooping down. It's not a 45-degree line, it's a curved type of a line. That means the contrast has lowered. Contrast is low for this line. As soon as we get this type of a curve, we will identify that contrast has been compressed, right? And again, for three color and black, I think it's pretty much the same, because see, where three color starts to droop or starts to get lowered, we start adding the black printer, right? Till the point where the three color is active, so that the overall density combination of densities is as per our expectation. Now, it's a very important thing that this curve is there. You see, normally what would have been the ideal nature of the curve? Somewhat like this, somewhat like this. But ultimately, even your four color reproduction of actual reproduction, realistic reproduction, is maybe capped at 2, right? It is maybe capped at 2. Now you may ask me, okay, but we have in order to overcome the deficiencies of the three color printer, I have added the black printer. So ultimately I was expecting a higher density, because when we add up the three color density and the black density, so black density is how much? It is maybe it is 0.6 or something, and three color density, it is maybe 1.5, sorry, 1.5 or something like that. Okay, so let me just it is more than, I think, 0.6, it is 0.7. So normally what would have happened if we were expecting the three color density was 1.5 and the black density was 0.7. So together, three color plus black, we were expecting an overall density of 2.2 for the four color representation, right? Four color tone response. But instead of 2.2, we are capped at getting a density of only 2. So that means what? The sum of the densities of the individual links is not equal to the sum of the not equal to the density of the combination through a particular filter. So that we know. Why is that? Because that is because of the additivity failure, right? And the reasons are very well known to you by this time. I've already explained in great detail in the previous lectures, right? Also, another thing I would like to mention over here is the fact that it depends, the maximum density that is achievable depends or varies with the nature of the paper that you are using. Basically, if you are using a normally a glossy type of a paper, you may get a overall density of 2. But if you are using an uncoated paper, then of course, because of diffuse reflection and first surface reflection, as you know, the density will be capped at somewhere between 1.5 to 1.7. So because of that also, the density is getting reduced, overall density is getting reduced, right? Now let us analyze the individual curves over here and what effect it will have. So now here, as you can see, that the overall nature of the four color printer, I mean the four color tone response curve that we have obtained over here, it is having low contrast, right? And another thing we have also noticed that in order to compensate for the, now you may ask, why is it getting reduced? The reason is that in order to compensate for the three color lack of or deficiency of the three color densities, the black printer is actually printing heavier black than is necessary, or greater proportion of black than is necessary. So ultimately what is happening, try to think about it, ultimately what is happening, if your black printer is printing greater amount of black than is actually necessary, as I told you already in the previous slide, that black is the dirtiest color, and even in the shadow areas over here, in the shadow areas we are getting very dark very high quantities of black. What will happen, we'll get higher quantities of blobs of colors printed. So if we want in half-tone reproduction very clear dots which are separate from each other, which do not basically increase in size, that is not basically happening over here. We are getting black, and because the black is printing heavier than it should have, what is happening, these patches and blobs of black colors are all over there, and especially in the shadow areas, the overall dot gain increases, and as soon as dot gain increases, you will not be able to find out the details. So if the details are not found, that means the tones are missing, and if the tones are missing, then the contrast is also less. I've already told you that contrast is basically a relationship of the tones that is present in the reproduction with respect to that of the original. So if your printers are printing heavier colors, greater density colors than is actually necessary, then what is going to happen? Excessive amount of ink patches will be developed. Now these patches will ultimately lead to dot gain, and the dots will get connected along the ends basically. And if this happens, what is the resultant of that? The overall the sharpness or overall detail of the particular image will also get reduced, and ultimately you will not be able to detect the different tones there, and ultimately the contrast is also going to reduce. That is exactly what has happened over here. And because of this factor also, you see, even in the mid-tone of the shadow areas, even in these areas also, because the black is actually printing heavier than the other color than is actually necessary, uh, the highlight areas, or even the not so much the highlight areas but the mid-tone areas especially, are also becoming more dirtier. And dirtier in the sense that it is printing heavy means that the density is higher than is basically required for the mid-tone areas or the highlight areas. So if that is the situation, then definitely there will be some dot gain and lack of detail that will face basically. So Because of all these factors, the overall contrast, why you may ask that the shape of the four color reproduction over here that is shown over here is drooping. The reason behind that is exactly this particular point, that the black printer is trying to compensate for the the deficiency of the three color reproduction, but in doing so, what is happening really is it is printing heavier than is necessary and reducing the overall contrast of the image. So this is not required. This is not required, and ultimately, what is happening? You see, the highlight and mid-tone shadows are getting reduced. Overall, there is a flatness throughout the image. Now, you may ask that okay, I may be okay even for the in the previous lecture, as I told you, we may be okay with a reduced contrast in the shadow area. I may even allow that, okay. But are we really okay with reduced contrast for the in the this thing in your highlight or the mid-tone areas? Are we really okay with that? No, we can't be okay with that. Even if the tones are compressed in the shadow areas, because of course over here as you can see the tones have been compressed, and especially in the shadow areas as well as in the mid-tone highlight areas. I may be fine with if the tones are compressed in the shadow areas, right? Because that is not that much identifiable or perceptible. Those individual tones in the shadow areas may not be that much perceptible by the human eye. But I am very sensitive to what happens in the highlight and the mid-tone areas. But in this situation, what we are seeing that since the black printer is printing heavier than is necessary, overall contrast in the highlight and shadow areas are also getting reduced. What is one way of uh, uh, increasing the highlight contrast in your reproduction? Any idea about it? Of course you should have an idea, because I have talked about this in great detail in the earlier lectures when we were talking about color correction using photographic masks. So I'll just pause the video over here for a minute, try to think about it, and you will get the answer. Obviously I'll give you the answer. If you use a mask, if you use a mask which is having a higher mask number, a higher mask number, if you remember, the higher the mask number, greater is your highlight contrast, greater is your highlight contrast, and lower the mask number, greater is your shadow contrast. So we'll use a mask number which is having a higher mask number. So yes, as we were talking about this particular curve over here, so as you can see that, as I told you earlier also, that if you want to increase the highlight contrast, you have to use a mask where the mask number is high. So in that situation, you will get a ultimate reproduction where you will find out there the highlight contrast is higher. And if you want increase in shadow area, shadow contrast, then of course a lower mask number is preferred. Okay. Now moving on to the next particular plot over here. So you will notice that everything in this part of the lecture, everything is based on plots. Everything is based on your graphical analysis. So because this is a very easy and quick visual method of identifying what the problems are in a particular reproduction. Okay. Now, in this till this time, we were talking about reproduction that is obtained in the ultimate or the final substrate. In this particular one, we will be talking about the film curve. If you remember the film curve that we talked about, that is the transparent. The reproduction is the transparency that we have just prepared using our process camera, whereas the original is your continuous tone photograph from which the reproduction was actually prepared. Okay. Now let us take a look at what we are trying to achieve over here. What this all this plot basically means. The idea that we have developed so far is that the behavior of your reproduction in terms of the tones that they reproduce is far from ideal, right? They will never be like the ideal plot that we are expecting, or they will never be as similar to the or same exactly same with that of the original that we have learned so far, and that is true for your film, that is true for your plate as well, definitely for your ultimate printed substrate. in this situation, in this particular one, we are trying to find out a way in order to first of all identify what is the behavior of our transparency with respect to the original, reproduce transparency with respect to the original, and how this thing can be basically made, the reproduction in the film can be made as close to the original as possible. Okay, now let us identify, now let us see what this curve is telling us first. What you have to do is, firstly you have to establish a baseline. For correcting anything, you need to know what is wrong, right? So if you want to know what is wrong, first thing what you need to do, you need to find out what is the right one, or what is the ideal behavior, right? So in case of any tone reproduction curve, what is the ideal curve? You tell me. A 45-degree line passing through the origin, that is your ideal curve. That should be your ideal curve in any, as a tone reproduction curve for any process basically, right? So, in order to find out what is the ideal behavior, or what is the problem in your tone reproduction, first you have to identify what should be the ideal behavior, right? Only when you finalize a baseline, after that you can compare the reproduction that you are having against that baseline in order to identify how much deviation has happened, right? So the first thing for us to establish is basically what is the nature, what is the overall nature of the ideal reproduction. So for that, what you need to do, you need to first point out or plot the minimum density that is available in the reproduction with respect to the original, and the maximum density in the reproduction that is present in the reproduction with respect to the original. So you have the printed sheet with you, you also have the transparency from which the printed sheet has been prepared. Now you need to compare that. What you need to do is that you need to compare the minimum, the least possible density that is achievable in your printed reproduction with respect to that of the original. So for example, in this particular case, what we have found, that the density in the original was, let us say it was 0.3. Okay, for a density of 0.3, what is the density in the reproduction? It is basically 0. So this is basically your minimum density that is achievable in your printed reproduction for the minimum density that is achievable in your, that is present in your original, right? Similarly, you have to do the same thing for your maximum density as well. So for a density of let us say, what is the maximum density that is possible in your transparency? Here you can see the maximum density that is possible for your transparency was, let us say it was 2.8. Okay, and what is the, for the same region, what is the maximum density that is possible in your reproduction? Let us say that is 2. For most coated papers, you will be limited to a density range of 2 only, so the maximum density will become somewhere in the nearby point of 2. So let us assume that your maximum density achievable in your reproduction is 2, and that is present in your original is 2.8. Okay, now what you have to do, you have to identify how to compress basically this low density so that it is you can say it is representative of the density range that is present in your original. So the point is that you have obtained the minimum and the maximum densities in your reproduction and in original. Now the reproduction of the straight line that is present over here would be considerably lower in contrast through the highlight and mid-tone areas than an ideal 45-degree line, and it would appear too flat and would have enough color printing anywhere in the mid-tone. Colored areas would have a faded look around them, and it will not look very good actually. The second method to determine the optimum tone reproduction for the color reproduction would be to assume a 45-degree line, which is this particular line that you can see over here. This is the 45-degree line, right? And since it is the perfect match for the original, to start at the highlight point with the 45-degree line and extend it up until it reaches the maximum printable density. That is what we have done. We have started from the minimum density and have reached to a point where it is having maximum density, maximum printable density, right? And then would actually give the reproduction that was not too satisfactory. In this situation, what we have to do, we see that this particular reproduction is not very satisfactory, but we want to increase density such that it matches with the density of the reproduction matches with the density of the original, which was 2.8. So what to do? We need to simply compress the shadow contrast so that the overall contrast, the density range that is reproduced matches with that of the original. Any tonal difference in the original shadow area will not be distinguishable in the reproduction. Detail will be lost and there will be large blotches of color lacking detail. Some of the small color differences between oranges and reds will be eliminated, and in general the reproduction will not look very good. In contrast, the contrast will actually be too high while the picture will print overall too dark. Now, the improvement would be made in the reproduction if the 45-degree line were maintained throughout the highlight and the midtone till this point maybe. We maintain the 45-degree straight line till the highlight and the midtone areas, and then the plot in the shadow areas are rounded off, or basically they are compressed. Okay. By lowering the shadow contrast, by compressing the contrast in the shadow areas, we are maintaining some of the tonal difference that were lost in the when we are reproducing the 45-degree line, and when the 45-degree line was not curved to the shadow point of the transparency. Okay, and this approach is quite satisfactory in nature. That means now you understand the reason why in the first in the earlier lecture, in the first slide, I told you that it is okay for us if we slightly compress the shadow contrast, but we have to maintain the highlight and the midtone contrast very well. This is of paramount importance to any tone reproduction process or methodology. Okay. So, as it turns out that although this is one way of identifying what should be the ideal, what should be the nature of the ideal reproduction, tone reproduction, and how to utilize this in order to calculate what densities are possible using the production methodology that we have with us. But this is not that easy. This process is not that easy, and the method of, or the process of color reproduction is basically a process of compromise. You see, we are starting with a tonal range, density range, that is not achievable with our substrate first of all, right? Because when we are talking about the your continuous tone image, it has got a huge density range in comparison to that of the printed substrate that we are working with, right? This is point number one. Second one, the materials we are printing with, that is our printing inks, the subtractive primary inks that we are using, they are also very much deficient in by nature in the hue in the way they reflect light. Okay, and the densities that we are supposed to obtain using multiple inks together, they are not reaching the density as was expected. This we all know. Added to this fact that we are seeing any image in terms of halftone images. So there is a mixture of white areas, that is non-image areas, and printed halftone areas. So the total amount of light that comes to our eyes reduces the overall density further, right? So that is another problem. The transparency is already a reproduction of the original scene. As you can see in this particular slide that I'm going to show you next, in this one, here what has been done, a density range or density comparison of the transparency of the image with the density of the scene, that is the original, basically has been done. Scene over here is the original continuous tone that has been done over here. Okay. If you observe this carefully, what you will see that the transparency has exaggerated the contrast and the density range of the original scene. Moreover, the way in which the transparency is viewed will also make the difference. Overall, as you can see over here, the nature of the this is your ideal, this should have been your ideal curve. That is, the variation in densities of the transparency should be linear and proportional with that of the scene. But ultimately, what is happening within the transparency itself, you can see, you can observe over here, the density range has basically increased. Why? Because the nature of the transparency that we are using is enhancing that density range, and it is exaggerating that density range. So if we are going to prepare plates and ultimately print using the same these particular transparency set that we have just prepared, what will happen? Instead of compressing the shadow areas, what will happen? They will get exaggerated. Again, the same problem as I told you previously, over inking problem will happen in that shadow areas. Blotches of ink will appear, everything will appear dark, and overall, as you can see, there is an overall increase in contrast in the entire picture. But this will be marred by the fact that the increase in contrast in the shadow areas is excessively high. Remember how I told you that in order to compensate for the lack of the three color combination, how the black printer was printing heavy, and because of that the shadow contrast increased to a great extent, right? And overall the shadow contrast did not increase, actually shadow contrast reduced for a different reason of additivity failure. But in this particular situation, when you are going to print your image using this particular set of transparencies, because the shadow areas has been exaggerated, the density range in the shadow areas has been exaggerated, what will happen? Greater amount of ink deposition will happen in the shadow areas. Overall detail will be lost in those areas, and it will appear very flat in nature. The nature of the image that we will be observing will be very flat in nature. Okay, this along with another problem there is, that is how the human eye perceives color. This I think I have already told you in the previous classes also, somehow, that the way human eye perceives color, perceives the tones, and is quite different than what is expected. We, or the human visual system, is more perceptible to small changes in tones that exist in the, or that takes place in the shadow, that takes place in the highlight area, than that takes place in the shadow areas. This becomes more important from the standpoint that for the highlight and mid-tone to be correct than the shadow areas. That is why we can basically afford to reduce the your shadow tones more in comparison to your highlight and mid-tone areas. If I show you this, another problem from this information that I just told you, how can we analyze this, or how can we correlate this information with this particular curve? Here you see, the instead of the shadow and highlight, instead of the highlight and mid-tone areas to be exaggerated, here the transparency is exaggerating the shadow areas, but that is not required. Our human eye is not perceptible to very many changes in the shadow areas. What we want is greater amount of contrast in the highlight area, mid-tone area, than in the shadow areas, right? So this non-linear response of the human eye towards your light, especially in the presence of light, basically, especially in the excessive amount of detail perception in the highlight area than in the shadow area, also changes the way transparencies have to be prepared. So we have to prepare transparencies such that the overall density range, or the contrast in the highlight in the mid-tone area of the transparency is higher than that it is in the shadow area. Now I will show you another plot over here. As you can see in this plot, the same type of effect, the same type of plot that I have shown you earlier also. Here the highlight and shadow points have been plotted, right? Now the plot, two things. First is, what is the minimum printable density with respect to the original, or with respect to the transparency, which is this particular point, right? And what is your maximum amount of or maximum printable density with respect to the original, which is this particular point, right? And you draw a 45-degree line, and this is basically your ideal curve. But you are not supposed to print like this. If you print like this, what is going to happen? Your shadow contrast will be greater than the highlight contrast, and not even if it is not greater, it will be equal to the highlight contrast. And because of this, it will not serve our purpose. Which purpose? That to take advantage of the fact that the human visual system is more perceptible to highlight any small changes in the highlight contrast than it is to the towards the shadow contrast. So what we have to do? We have to find out an optimal tone response curve. How to do that? We basically have to identify, like we, if you remember, as we did in this particular one, this is basically your maximum density that is present in your or achievable in your original. Similarly, in this scenario also, we will do something. We will maintain the straight line section till the mid-tone, somewhere in the mid-tone area. Then we will start to basically compress the shadow areas. Why we need to do this? We need to do this in order to take advantage of the fact we need to maintain the straight line part of the highlight and the shadow as much as possible. Why? Because we need that higher contrast in the, just compare. If I tell you to compare one the curve number 1 and curve number 2 over here, whose contrast is whose overall contrast is higher? Of course that of the curve number 1, because it has got a steeper slope. I am saying that you need, in order to find out an optimal tone reproduction curve, you need to maintain the straight line section in the highlight as well as in the mid-tone area, while compressing the tones in the shadow area in order to take advantage of the human visual system and how it perceives light. Okay. Now, after this, what you have to do, you just connect the highlight and the shadow points while doing most of the compression of the tones in the shadow areas, and maintain a contrast of 0.9, which is slightly less than the 45-degree line. If here the gamma was 1, here the gamma will become 0.9 in the, at least in the shadow and the at least in the highlight and the mid-tone area, which will preserve the contrast in the highlight and the mid-tone area while compressing most of the compressing the contrast compression in the shadow areas, right? In the shadow areas. But another thing you have to consider, that when you are printing on porous substrate, porous media like your newspaper, which is, or even your map litho paper, which are very porous, and the percentage, the chances of dot gain is higher, then you have to keep in mind that you have to lower the mid-tone contrast slightly more in order to prevent the extreme compression of the tones in the shadow areas. What is going to happen there, you know, that in such a media where, for example, you are printing a newspaper where the chances of dot gain is very high and the contrast will be further lowered, or in map litho paper where the same problem occurs because the contrast will already is getting lowered, so what will happen to the tone response curve? Instead of this type of a curve, the curve will become somewhat like this. So initially what we considered that, okay, fine, I will compress the shadow tones, but I will try to preserve as much as the highlight and the mid-tone areas as possible, right? That is what we have considered. But now, and that is why the gamma of the straight line section in the ideal curve was 1, and that in the tone reproduction curve that we just prepared became 0.9. But when we are printing on very porous media, poor quality media basically, then there is a chance that the contrast will get reduced further. And which contrast? Not only for the shadow contrast will definitely go down, but along with that, the mid-tone contrast will also go down. So in order to keep while printing in that, we need to lower the mid-tone contrast slightly more, so that the contrast reduction in the shadow area does not become too high. We do not want a an overall contrast like this. We do not want a curve which appears to be like this, where the contrast has been reduced to such an extent almost no discernible no separate tones are discernible in the shadow areas. We do not want a curve like this. So what we do, we reduce the mid-tone contrast more and keep the contrast compression in the shadow areas to an optimal extent, so that there is not overcompensation or over compression of the contrast in the shadow areas. This we have to keep in mind. Okay. Another important point that I would like to mention over here, see, if there is, here we start from a point which is basically your considered to be the minimum print density, right? Minimum print density versus your minimum density that is present in your original, right? Here the transparency we are using nonetheless, but this is what this point basically means. Now the nature of the curve should not change much. The overall nature of the curve that I have pointed out in curve number 2 that have been drawn over here, this should not change much. The till the the mid-tone areas and all, the nature of the curve should perhaps remain in straight line part only, with very minimal compression in the shadow area, right? But there is a chance of movement of the overall curves either left or right. Why is that? That depends on the minimum density that is achieved in your that is present in your original. So for example, if your original has got or is starting from a density of 0.6 maybe or 0.5 maybe, whatever it is, then your curve will move rightward, and if it is moving or it is having a density as low as 0, then it will move towards the left. So there is a chance of movement of the curves in the towards the sideways, that is left and the right side. Okay, so this is another thing that you have to keep in mind basically. Now we have seen till now that the scale that we are using in these particular curves while plotting these particular curves, these curves or these scales are basically linear in nature. Okay, that means the interval between two consecutive graduations remains constant. It does not change. In this case it is 0.4, so difference between these two graduation is 0.4, between these two graduation is 0.4, between these two graduation is also 0.4. Similarly for this also 0.4, this also 0.4, etc. But do you think that this is of much help? Do you really think that this is of much help, or this will do any this will provide a good perspective of how, the optimal tone reproduction curve in terms of the human visual system? See, I have already told you previously also that the human visual system is more perceptive of the small changes in the highlight and mid-tone areas than it is in the shadow areas. But here we are stuck with a scale which gives equal weightages or equal intervals between the shadow area, between the highlight areas, mid-tone areas, and shadow areas. So we need a scale, or we need a graphing system, a plotting system, which will take into account that human visual system. This type of a graphing thing was developed by H. Brent Archer at RIT. Okay, and there you will basically see what the graduations. So you may just pause the video here for a minute, take a screenshot, and you may zoom out a little bit so that you can see. So here you see, this is basically the density similar, the x-axis remains the same, independent axis density of the original, and here you have the density of the reproduction, right? But look at the nature of graduations. What do you notice? The intervals in this area, what is this area where the density is low? Which area is this in the image? That is the highlight area. This is the mid-tone area. This is the shadow area. Now you see the interval between two consecutive graduation in the highlight area, this one, you compare this interval and you compare this interval. This small intervals between the two graduations between two graduations in the shadow area and in the highlight. What is the distance between two graduations? What is the interval between two graduations in the shadow area and in the highlight area? Now remember, if you take a look at the previous slide over here, as I told you, in the highlight area also the interval was 0.4, in the mid-tone also it was 0.4, in the shadow also it was 0.4 for both the axes. But in this case, what you are noticing here, the greater emphasis or greater interval is there in the shadow area than in the highlight area than we are giving in the shadow area. That means even if there are smaller changes in the tone reproduction curve in the highlight area, there will be greater change that will be noticeable if we plot that tone reproduction curve in this particular curve than when we plot in this particular curve. So now what is going to happen in this particular, so let me just put this into perspective and let me now listen to this very carefully. Okay, now you see a change of 1 inch in the highlight is an equal visible density change as a change of 1 inch in the shadow that was in the previous one. But the densities here are not equally spaced, right? In this, what I am saying is, although the change represented between two graduations remains the same, but the density change is not equally spaced. That means greater changes are present in the highlight area than in the shadow areas over here. Okay, this is the graph paper that allows us to plot the tone reproduction curves in terms of the human visual system. A very small bow in the, that means a tilt in the curve of the graph plotted on a normal graph paper in the highlight might not seem significant, but visually in the reproduction it may be more noticeable, it may be more perceptive. As I told you, if you compare the, let me just clear this out so that you can understand this. Let us say here you see the in the highlight area the curve graph has tilted slightly. Now imagine plotting the same curve or same tilt in this particular curve. So I'll just draw side by side. Do not see, I'll just try to draw side by side. Now curve that previously was like this may look like this in this particular curve. So this particular curve was the curve or tone response curve that was obtained in the previous graph, but this is the actual curve that is obtained in the, so let me just redraw this. This is not a very good way, this is not a very good way of drawing, so I'll just redraw this. So what is going to happen is that it will actually appear like this, like this. Try to understand, these are the TRCs of the same reproduction, the tone reproduction curve for the same reproduction. One is basically the tone reproduction curve when we draw this in the previous previous graph. But when we use this kind of a graph, which is a representation of the human visual system, then the TRC appears to be like this. So here you see there was very slight change in the highlight area. It was almost a straight line, but greater change in the shadow area, right? Here, because the density interval is more spaced out in the highlight area in this particular curve, in this particular graph, that is why the change in the highlight areas are much more pronounced or much more prominent in the highlight area, and because the changes in the shadow areas were not that prominent and the density intervals are very small in your shadow areas, it becomes almost linear in nature. This is a very good representation of how we perceive tones, because we perceive greater amount of tones, or we can perceive even very small changes in densities in the highlight area than that we can perceive in the shadow area, and that is exactly what is happening over here. And similarly, the tone compression that is evident when plotted on a normal graph paper like the previous one, it will not seem as drastic when it is plotted in this particular one. Here you see, that is exactly what I told you earlier also. There was a tone compression in the shadow area, maybe like this, there was a tone compression in the shadow area, but here in this particular graph paper, where the shadow areas have got minimized because the density intervals have been lowered in while representing the shadow areas in this particular graph. The changes in the shadow areas are not that much visible. I mean, this is, I just demonstrated you, this is not the actual curve, but just to make you understand that the change that you are observing in a normal graph paper in the shadow area will not be as drastic as when you plot the same in this particular graph paper, right? So this is another method through which we can basically understand, or better way of basically identifying the actual nature of the tone reproduction. Okay. Another important thing that I would like to point out over here is that, see, we are always talking about contrast in terms of the slope of the straight line, but there is more to this than that. Here, it all depends of the nature of the where the curve begins is also very much important. Okay, if you manage to achieve the correct contrast, but you seem to misjudge the location of the highlight, that may end up making the entire reproduction very dark, as I was saying in the previous slide also. So for example, you have not plotted the highlight minimum achievable density properly in your curve or in your graph, as a result of which your graph has shifted a little bit towards the right hand side, right? That means initially your graph or plot started from this point. Now your plot is starting, let us say, from this particular point. Okay, so if this is your nature of the curve, then don't you think the entire reproduction will become too darker? Overall density will increase throughout the image. For the best possible reproduction, a 45-degree ideal situation is a 45-degree line. Now, the misplacing of the highlight would move the entire curve up, making each density of the original appear darker than the reproduction. This you have to be very, very much careful about. Okay. So this is perhaps one of the last important points that I wanted to highlight. So hopefully whatever I have told you is clear. In the next lecture, what we are going to discuss is that till now we discussed about the analysis of the printing process and the determination of the optimal tone response curve. Now we will be discussing that how to implement this tone reproduction curve, actual optimal tone reproduction curve, in while the print production we are going to do. So till now we have developed a sense of what is the nature of the ideal tone reproduction curve and what is the nature of the optimal tone reproduction curve, and the compromise basically. Now we are going to implement this tone reproduction curve while our print production workflow. That we will do with the help of a tool which is known as the Jones diagram. So in the next lecture, we'll be talking about that only. All right. Thank you for listening.